Welcome to Darwinian Bytes, where we explore the world of evolution and emergent behaviors through computer simulations. In this video, we're going to continue introducing movement to the simulation by expanding the movement algorithms to slightly more complex algorithms. If you haven't seen the first part of this video series, I would recommend watching it now, as it also explains the core algorithms that we're going to be using and how they're integrated into the framework and the simulation. With that in mind, I'm going to quickly recap the previous video to help refresh everyone's memory of where we left off. First, the rules of the simulation, at least before any movement algorithms were added. Entities can be either the color red or blue. Entities can be of size 2 pixels to 20 pixels. Entities can consume smaller entities of a different color. Entities of equal size have a random winner. The winning entity increases by 2 pixels and the losing entity decreases by 2 pixels. Entities spawn another entity when they reach a size of 20 pixels. Both the old and the new entity are of size 10 pixels. Entity of 0 pixels die and are removed. Entities have an eyesight of 100 pixels. If there is no smaller entities in its eyesight, then an entity randomly moves between 1 to 7 pixels in a random direction, left, right, up, or down. If an entity sees a smaller enemy entity in its eyesight, then it will move towards it between half a pixel to 3.5 pixels, half the normal movement. There are no avoidance rules. If a bigger enemy is within its eyesight, it's not even aware of it. In the previous video in this series, I go over how the code is architectured and so on. I also go over the concepts of vectors, which we'll be using again here in this video. So if you haven't yet had the chance to view that video, I recommend doing so now. The link is in the description. To quickly recap from the previous video, the simulation is programmed so that we can easily swap the movement algorithm. The movement algorithm itself just has one method we need to override called move with entities in eyesight, which takes the entity being analyzed as well as a list of all the entities within its eyesight. From there, the algorithm has a number of helper methods, such as filter the list of entities to just enemy or friendly entities, or to find a larger or smaller entities, and so on. As well, there are a number of helper movement methods, such as move away from entity, which does all the calculations so we don't have to worry or even remember how they work at this level. Basically, the code has been set up so that we can quickly and easily focus on what we want to do. I'm just going to very quickly go over the movement algorithms we covered in the last video. I'm not going to go in any kind of detail, except for maybe the last one because of the emergent behavior that resulted from it. For the full details, I'll refer you to the previous video, again with the link in the description. The first movement algorithm we covered in the previous video was move towards the smallest enemy. This is one of the most simplest movement algorithms that are possible, and the result was pretty similar to the original simulation. The main goal here was really more just to confirm that the movement framework worked as expected. The next movement algorithm we covered was move towards the nearest enemy. The goal here was to help reduce clustering. It doesn't eliminate it, but it does help reduce it. There's some other interesting behaviors where battles can oscillate back and forth, but I'll leave those details to the previous video, as it goes through an example to explain why this happens. The next movement algorithm we covered was avoid nearest enemy. In essence, instead of seeking the smaller entities to consume, entities would just avoid bad outcomes for themselves. The biggest effect of this movement algorithm is that there are almost no battles, and so the simulation never ends and just goes on forever. One interesting and very unexpected behavior is that if I increase the population from 1,000 to 10,000 or more, that after around 1,000 to 1,200 generations, the simulation would almost always end up looking like an animal print. And although the details of the animal print pattern would slowly shift and move with time, the overall animal print pattern would nonetheless remain. Which leads us to today's video, where I want to cover 3 new movement algorithms. Move towards nearest smaller enemy and avoid nearest bigger enemy. Move towards smallest enemy and avoid the largest enemy. And move towards the average smaller enemy and avoid the average bigger enemy. If you haven't noticed, all 3 of these movement algorithms combine 2 simple movements together. On that note, I'll just quickly say that more advanced movement algorithms, such as predictive seeking and so on, will be covered in a later video because they require concepts like velocity and acceleration, which the simulation doesn't yet have. Move towards the nearest small enemy and avoid the nearest big enemy is similar to the previous movement algorithms, with the exception that we're combining two algorithms instead of just doing one. We're basically combining the two movement vectors from the two different movements to give us our final movement vector. In more detail, we're taking the vector of the nearest smaller enemy and then subtracting the vector of the nearest larger enemy and moving in that direction. The code also has to be adapted a bit. We can't just run one of the previous movement algorithms after the other. Well, technically we could, but it would be inefficient, more complex, and just plain ugly in my opinion. Instead, let's try to combine them in a nice, clean, and simple algorithm. First, we want to filter out the list of entities in our eyesight to only be enemy entities. If there's no enemies, then we do a random movement. Assuming there are enemy entities in our eyesight, then we want to get both the closest small entity and the closest large entity. The first stream filters out the list of smaller enemy entities from the enemies list, and then gets the closest one from that list. Similarly, the second stream does the same, but this time it's looking for the nearest bigger enemy, assuming there's one or else null. We then call the method moveEntity relative to other entities, which takes three arguments. The first, the entity that we're calculating for, then the second, the entity we want to move towards, and finally, the entity we want to move away from. That code then calculates the total resulting vector and assigns it to our entity as its next movement, including calculating how to wrap around the screen and so on. I'll begin by saying that the movement algorithms in this part 2 of the video series are all overall more interesting than those in part 1 of the series, not counting, of course, the one that resulted in the animal prints. As you can see in the simulation that's running now, there's several more obvious and interesting behaviors emerging from these new movement algorithms. The most obvious is very large entities surrounded by smaller entities avoiding them. This is mainly because once they reach a certain size, almost no remaining entities can consume them, so everyone is essentially running away from them. But only up to the distance of the entity's eyesights, which is why we get circles around them. There's also a lot of non-obvious behaviors going on in these circles, and I'll only cover the tip of the surface, otherwise this video would get way too long. What I'll say is that if you think about why certain behaviors happen, then a lot more of what is happening will make sense. Let's start by covering direction. That is, why are the entities going in a certain direction? As in, why is the blue entity going down at this moment? Well, if I were to rewind the video a little bit, we would see that it all started when a smaller red entity got squeezed between two larger red entities, at which point the chase was on. And then anytime another entity noticed the bigger one, it would get out of the way. Meaning, the smaller entity it was initially chasing was always the closest entity, until finally at some point, by random luck, another red entity got close enough which caused it to start wobbling. Eventually though, a red larger entity finally crossed the blue entity's path, at which point the blue entity had to run away itself, forcing and pushing its direction much more strongly. Now, if we take a moment to think about it, that means the red entity should catch up to it eventually. Now, why do you think that is? If we go back to our vector math, unless the nearest smaller entity is directly opposite of the larger red entity, then the blue entity will not be moving directly away from the larger red entity. It will be moving somewhere in between. And since the red entity is directly seeking and not avoiding, it will catch up quickly. If there were more entities around, then it would be influenced by other entities, but in this case, it's just a matter of time before the red entity catches the blue entity. In this particular case, we don't have to wait that long. A second bigger red entity joins the party, which in turn forces the blue entity to be squeezed. Just a quick comment before I go on to the next behavior of this movement algorithm. I just want to remind you all that this movement algorithm says to avoid the nearest larger entity. It doesn't take into account what happens if there is a second larger entity nearby. it only takes into account the nearest larger entity, which is why the blue entity ran almost directly into the second bigger red entity. It doesn't even take it into consideration. This is one of the issues with this movement algorithm. Since we're already looking at the end of a simulation run, you might notice that it can take quite a while for a simulation to end, especially if an entity is the largest possible size. Eventually, it will run into an equally sized entity, assuming there is one, in which case things will change, and depending on the winner, may end the simulation quickly or may extend it. Also, of interest compared to the previous movement algorithm is that the winner and loser rarely switch. That is, once one color is winning, it tends to win out almost all the time. Not always, but the vast majority of the time. Getting back to the simulation in general, I'll quickly point out another interesting behavior where entities tend to form lines. I won't go into details of why it happens. I'll leave it as an exercise to you, the viewer, but I'll say that if you use the same logic that we just went over for the chasing behavior, it all makes sense. I'm looking forward to reading your analysis in the comments section. On a side note, it's much more observable when I increase the population by tenfold, but more on that shortly. The next thing I want to talk about, and it's the most interesting behavior I've noticed to date, is what I like to call glitches in the simulation. It happens pretty rarely, maybe only once in every 5 simulations. In more detail, a small number of entities get into a configuration where they are stuck and can't move. They are perfectly balanced between seeking and avoiding. It generally happens in the form of a line because the math works out that it's much easier to get in a stable configuration that way. But in some very rare occasions, the glitch will happen in a configuration beyond a line like this one. This is the glitch I found the most interesting, so I think it's worth taking a moment to analyze it. Let's start by rewinding it a bit so we can see how the glitch initially formed. You'll notice it actually started with a line glitch. Then a red and a blue entity added to the glitch. The blue and red entities eventually settle into a stable state. As the simulation continues, other entities keep joining the glitch, all the while keeping it stable. In case you hadn't noticed it, that bigger blue entity is what is keeping the larger red entity at bay. I'll fast forward a little bit so that you can see how stable it is. In fact, more entities join and are added to the glitch. This stability is maintained for quite a long time until eventually a larger red entity gets within range, which then finally disrupts the whole configuration. But why was it so stable? Well, let's zoom into it and add some vector arrows to get a better understanding of what's going on. This won't be super precise since I'm doing it after the fact, but it should be good enough to explain what's going on. I'm also going to ignore how the glitch started. I'm just going to focus on how it's being maintained. Now, before I begin, please keep in mind that there can be smaller entities under the larger entities. For example, this red entity could be comprised of many entities of different sizes, meaning some entities can be both repelled and attracted to the same location. Assuming we now understand why the larger outer entities are locked in position, it then makes it easier to understand why the smaller entities in the middle are also locked into position. If we just look at one line, it's a lot easier to understand, at least at first. Although it's hard to see, the vectors are all basically just canceling each other out. This glitch is interesting because it gets a lot more advanced and complicated. We're now also dealing with angles and so on. The odds of balancing all that gets a lot more challenging, which is why they happen so rarely. Linear glitches happen about once every other simulation run, whereas non-linear glitches like this one happen at most every 5 to 10 simulation runs. So they are much rarer. They also don't tend to last. This one is exceptionally special and rare because I only saw it happen once in all the simulation runs, because of both its form and how long it lasted. We'll end the analysis of this movement algorithm by running it one last time, but with 10 times the entities this time. That is 10,000 entities instead of 1,000 entities. Overall, it's very similar. However, the lines of smaller entities are much more common and much easier to see. As well, it's easier to see clusters of smaller entities like this one. Overall, it's very similar to the regular population density of 1,000. The main difference being how much more visible certain behaviors of the smaller entities tend to be. You see the same lines in the normal simulations, but not as often, and they tend to be smaller and less obvious. With a higher population density, they definitely do become more prevalent, especially if you speed up the simulation. I think this is because as the population density increases, there's a lot less random oscillating, as most entities tend to be either seeking or avoiding, which is why behaviors like the lines tend to be more visible and apparent. This code is very similar to the previous movement algorithm, with the only change being that we now move towards the smallest enemy while also avoiding the largest enemy, instead of focusing on the nearest ones. As a result, the code is almost identical except for two lines, the min and max lines. Although you would think the behavior of this movement algorithm and the last one would be pretty similar, and in some ways they are, but in other ways they're quite different. In terms of similarities, for example, there's still quite a few circles. In fact, they can become a lot more pronounced if the population density increases. But the lines have mainly disappeared, even with the higher population densities. In fact, you'll notice that the smaller entities in general don't survive. This makes sense because we're now looking for the smallest enemy entities instead of the nearest smaller entities. Another big difference is that the glitches are gone. I only saw a single glitch, and it was barely noticeable at that. Glitches just don't seem to happen anymore. Something that's also interesting is that not a single simulation I ran ended on its own. There was always at least one big entity that would continue seeking forever. Sometimes there would be a few remaining big entities, but eventually it would always go down to a single larger entity that was never consumed or squeezed between other entities. Now, the simulation could be adjusted by changing the filters to look for smaller or equal-sized entities instead of just bigger entities. And in fact, when I did do this, the simulation definitely ended. What was more interesting though is that the circle patterns rarely lasted because another big entity would always quickly start pursuing the larger entity until there was a collision. So although the circles still happened, they definitely did not last anywhere near as long on average. And again, all the simulations ended. As you've seen from the last two movement algorithms, one big glaring issue that still remains is what happens when there's a second bigger entity nearby because it's ignored by the movement algorithm, which only focuses on one entity to avoid at a time. Specifically, if there are two bigger entities, only one is taken into consideration. Therefore, we need to be smarter. There's several approaches we could take, and we could be quite smart. But for now, since we're just going to introduce the concept, we're going to go with a pretty naive option and leave the more complex options to a later video in the series. Specifically, we're going to take the average of all the smaller and bigger entities and just add them up. Just a quick example of how we could be smarter is that we can also take into consideration their distances and add a magnitude based on that. But for now, since we're only introducing the concept, we're going to go with the most naive option and just take the average of all the nearby entities within an entity's eyesight and see where that leads us. The code changes for this behavior algorithm turn out to be very simple because of our previous efforts. In fact, the code is simpler than the previous two movement algorithms. The key reason is that the helper method we had previously created, which was called move entity relative to other entities, can take a list of entities to move towards and away from and do all the vector math for us, which means calculating the average movement. Therefore, our code is as simple as just getting a list of smaller enemies minus the comparator to get the smallest distance or size, and then getting the list of the larger enemies minus the comparator for the size or distance. We then send those two lists to the move entity relative to other entities method, and everything is taken care of for us. It's nice when more complex methods and algorithms end up having smaller and simpler code. Now, let's get into the behavior of this movement algorithm. The first thing I notice is that although it has a lot of similarities with the previous two, is that it feels better and more natural, for lack of better words. For example, if you were to pretend the entities are, say, fish, and that the bigger fish are hunting smaller fish while trying to avoid being eaten, then the behaviors on the screen look a bit more realistic than before. Not entirely, but there's definitely an improvement. For example, and although it can happen that a smaller entity will go towards a larger entity because of bad luck, it happens a lot less and it just feels more natural overall. Again, it's not perfect. We can definitely improve on it, such as adding a magnitude, but this feels like the best movement algorithm we've seen so far. With that said, let's get into some more details. About half the simulations never ended. The short version is that because bigger entities are always looking for smaller entities rather than smaller or equal to entities, that when it comes down to the last entity, it's either squeezed at that moment or it will never be squeezed from that point on. And this tends to happen about half the time. Something else that's less obvious just watching the highlights as we're doing here in this video is that there are a lot more interactions between the entities. Again, for lack of a better word, the entities feel more lively and more natural looking. As a result of the more frequent interactions, there's also a lot more squeezes between the entities. That is where an entity gets caught between larger ones. I'm sure that you're thinking if it was real life, they would have just adjusted their path. And you're right. If we go back to this example, you'll see that the average path is not ideal. Instead, a better option would be to move in this direction. So there's definitely room for improvement. On that note, the glitches seem to be completely gone. At least I didn't see one over all the simulations I ran. Also, smaller entities are much less common. As well, once one side was leading by at least 70%, it never lost. Those lines I was mentioning before are also generally gone except for the circles around the larger entities. And even those are a lot less common as they tend to be broken up fairly quickly on average. When I increase the population to 10 times, that is 10,000 entities instead of 1,000 entities, we almost immediately start to see clustering at the start of the simulation, which we really haven't seen since the last video. The clustering doesn't last long, barely a few hundred generations, maybe about 10 seconds, but it's definitely there. Something else we see with a higher population density is a bit of a comeback of the smaller entities, but they're much smaller in number and frequency. They're there just enough to show they can exist. Instead, what we see is a lot more clustering. That is, we're going back to having a large number of cluster battles that seem to last for a long time, which is a bit less ideal and not really what we want. The other thing with a high population is that entities can't really last long before they get squeezed by some kind of random scenario. I actually find it interesting how different the behaviors are between the lower and higher population densities, but that's something to investigate on its own and not for today's video. Overall though, this movement algorithm is probably the best looking scenario so far, even if it still has some issues. It feels and looks more realistic. Again, as I mentioned before, there's still situations where the entity should obviously be taking another route, and using magnitude would definitely help, as well as some smarts, but so far I would say this is probably the best movement algorithm. I'm thinking the next video in this series may be a battle between the different movement algorithms we've already covered, since in general they are all pretty naive and follow simple rules with no computed calculations or smarts. I think it would be interesting to see which one would win, and if they would win consistently. Each movement algorithm would of course have its own color, so that we can see which ones are winning, and, more importantly, if they're consistently winning. On that note, I'll end the video by asking you to predict in the comments below which movement algorithm you think would win between all the different movement algorithms we've covered so far. And don't forget to like and subscribe to see more contents like this.